Hello Year 12s, this is Mr. Lim again with another WACE exam questions video, just going through some of the WACE exam questions so that you understand what's going on. Alright, so here's a multiple choice question. Again, this is the video that you would watch if you don't really get this one. This is the average that everyone scored, so it tells you a bit of information about how hard it was or how easy it was. And then this is some notes from me or from the examiners to say what you can do better next time. Right, so when a piece of indium metal, In, is placed in some acidified dichromate solution, a reaction occurs resulting in In 3 plus ions being produced. The equation for this reaction is shown below there. All right, the EMF of this reaction is 25 degrees Celsius, found to be 1.70 volts. Okay, so it just means it's at standard conditions. All right, so you've got 1.7 volts being created from the redox reaction here. So what I've written is that you identify which is the oxidant and which is the reductant, and then you have to work out whether it'll be higher or lower than the dichromate reaction. Okay, so let's have a look here. You should recognize the dichromate reaction. Okay, that's on your standard reduction potential table. All right, it's on the standard reduction potential. The dichromate going to chromium ions is at positive 1.36. Okay, so we should recognize that if it's going in this direction with the electrons on this end, it is gaining electrons, so therefore this is the reduction. Okay, we're happy with that. Okay, therefore the other reaction must be the oxidation, and we should also be able to tell that because, well, it goes from a In to In3 plus. Okay, and making 3 electrons over here. So we should recognize that that's the oxidation. All right, so we should also recognize that if I was to write this on the standard reduction potential table, I would have to write it backwards. So this would be In3 plus, and this would be In solid, and the 3 electrons would be over here. Okay, just if I'm writing it as if it was on the standard reduction potential table. And I should recognize also that I have to have a downhill arrangement. So therefore that reactant and that reactant should be in that orientation. Which means that this indium reaction should be below the chromium reaction. Because if it was above it, it would be in the uphill orientation. Okay, because if it was above it, it would be like that, and that would just be wrong because that wouldn't work then. Okay, it wouldn't be a spontaneous reaction. So we know that it is below chromium, right? And we know that it's going to be the difference between these two is going to be 1.7 volts. All right, so if the difference is going to be 1.7 volts, what number gives us a difference of 1.7 volts? It's going to be a number negative 0.34. All right, and that's that one there. Okay, so a couple of things. Identify which is the oxidant, which is the reductant. Right, think about which one needs to be written backwards, and then which one is going to be above or below the other, following the downhill kind of rule. All right, and then work out, using the difference, work out what the value is. Okay, and this question I anticipate will come up again in the 2020 exam, so please make sure that you understand how to do this one. Right, so again, this is the same question, except this is the following question. You need to work, again, this is answer slightly better. You need to work out the voltage value for indium at the last question and then use the standard reduction potential table to do this. Okay, so we worked out that the value for indium was negative 0.34 volts. Okay, and without this, you can't really work out the rest of these. Okay, so which of these following sets of metals cannot be oxidized by the indium ion? Okay, so the indium ion is on this side because all the ions are on this side. Indium there. All right, so we want to find out a metal that cannot be oxidized by indium. So do we want to be looking for metals below or above the indium? We want to be looking for metals above the indium, okay? Because we want it to not be able to be oxidized, so therefore we want that uphill configuration, okay? So if we want that uphill configuration, we need to find metals that are above 0.34 volts, okay? So which of them cannot be oxidized by indium at positive 0.34, you would have to just do a process of elimination. So tin is at negative 0.14, so yes, that cannot be Cadmium is at 0.4, so that's below it, so that's going to work. Magnesium, definitely going to work. So that's not going to be it. All right, so we know it's not A, we know it's not B. Manganese at negative 1.18, so that's not going to work. So, well, that is going to work, so which means it's wrong. And then the last one, nickel, tin, nickel at 0.24, tin at 0.14, copper at positive 0.34, and silver at positive 0.80, so it's this one here. All right. So just the process of elimination going through, and once you've eliminated one out of that list, you really don't have to go and check the whole list. All right, so that's how you do that one. This is oxidation number. You just need to make sure that you know how to do oxidation numbers. All right, this one here, negative 2 of them, so it's negative 4. It's an ionic substance, so it's 0. So what plus negative 4? Positive 4. So this one's positive 4. This one here is, what's that going to be? Positive 6. And this one here is going to be, let's have a look, negative 2, negative 8 in total equals negative 2. There's a positive 1 over here. What plus that makes negative 2, so that'll be positive 5. Okay, so positive 5, positive 6, and positive 4. So we're just going to put them in order. Just really make sure that you're reading the increasing. So you want that one first, that one second, and that one third. And that's this one, D. All right. Yes, right? Yep, that looks about right. Okay, so increasing oxidation number. Displacement reactions. Okay, so a group of students decided to investigate the reactivity of 4 different transition metals, these 4. They did it by placing small pieces of metal, which is effectively a displacement reaction, into their solutions. Right. Blah, 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 blah. So, which of these metals is the most easily oxidized? Okay, so remember, oxidize means metal turning into an ion. So then we have to look at which metal always turns into an ion. Okay. It is zirconium. Okay, because the reaction occurs every single time. So it's the most easily oxidized by all of the other ions. Right, so the zirconium is the one that is easily oxidized. So there you go, 14C. Right. Again, same question, but instead it's asking for the weakest reducing agent. So, strong reducing agents can reduce other substances. Which metal cannot reduce any of the other ions? Okay, so remember, reducing agent causes reduction. So a strong reducing agent can reduce a lot of other things. So which one cannot reduce anything? Meaning that it is the weakest reducing agent. It's the one that cannot reduce any of the others, which creates no reactions, which would be rhenium then. Okay, and so therefore it's rhenium. Because there's no reactions here, here, and here. All right. Okay, watch the video or ask questions if you don't really get that one. Okay, it's really just making sure that you understand your vocabulary as well. Okay. Which of the following statement pairs can be used to distinguish between an electrolytic cell and a galvanic cell? Is pretty much identifiable ones which are wrong statements. Okay, both of these statements are correct. Okay, let's just check all the other ones. Oxidation occurs at the cathode. No, it doesn't. It occurs at the anode. Oxidation always occurs at the anode, no matter what type of cell you've got. Ions do not migrate. No, ions still migrate. They still move around. And can be used to power a battery. No, not really. You can't power stuff with an electrolytic cell, and you can't electroplate stuff with galvanic cells either. So it's A. Okay. Okay. So an example of a galvanic cell is a molten carbonate fuel cell, represented in the diagram below. As the cell operates, hydrogen gas is reacted with carbonate ions at the anode, while the oxygen gas reacts with the carbon dioxide at the cathode. The carbon dioxide gas is reused. Okay. Write the half equation to show the reaction at the electrode at which oxidation occurs, which happens to be the anode. Okay, so the notes from the examiners say, in part A, many candidates simply remembered that standard oxidation for the half cell and quoted the equation H2 goes to 2H plus and 2E minus. Okay, so what they've said is that, okay, well, all I remember about fuel cells is that hydrogen turns to hydrogen ions, and that's it. Right, so they've just gone, yep, hydrogen goes to hydrogen ions, but you haven't taken into account what this diagram is showing you. Because this diagram is showing you, and even the text, is that if this is the anode, if this thing here is the anode, right, you've got hydrogen gas and carbonate ions combining together, and it even tells you so in the thing, right? So if you've got those two things combining, you've got to have them in the half equation. So H2 plus CO3 2 minus turns into CO2 plus H2O. Okay, and you've got to go balance all of these things. So, look at that. Everything is balanced. All the elements are balanced. The only thing that's not balanced is the charge. Right? So, since the charge isn't balanced, you have to look at the charges. Total of -2 on the left and 0 on the right. So therefore you add 2 electrons on the right to balance that up. Okay, and that is the half equation to show the reaction. But the idea is that you just don't go and say, oh, fuel cell, hydrogen. No, you have to look at what is given you. So again, how do you write the half equation? You have to look and find out what's the oxidant, what's the reductant, what's the reactant, what's the product, and then put it all together. Okay. So look at the next one. Okay, so write the overall equation for the current producing reaction. Okay, exact same thing. So we have the half equation from before, so let's just go rewrite that. H2 plus CO3 2 minus goes to CO2 plus H2O plus 2E minus. That was from the last question. Now we have to work out the reduction equation, the reduction reaction. Okay, so the reduction reaction, we've got oxygen. But is that the only thing? No, it's also got carbon dioxide. Okay, what does it turn into? Carbonate ions. Okay, so you've got to balance this equation. First of all, you balance out the carbons. Yep, they're balanced. Then you try and balance out the oxygens. Except you can't, because instead of trying to balance out the oxygens, what you can try, because you've got oxygens here and oxygens here, you don't need to just add water, right? What you can do is work out that if I double this, I can double that, and now I've got the same number of electrons, so oxygens on both sides. Okay, so I've got 6 oxygens over here and 6 oxygens over there. All right, so if I have all of the oxygens balanced, this is a balanced equation, except now I need to go add 4 electrons to this side to balance out that equation. All right, so done that. Now I got to combine them, so you got to find the lowest common multiple. Happens to be 4, so this one has to be multiplied by 2. Multiplied by 2. So therefore, the overall equation will be 2H2 plus 2CO3 2 minus plus O2 plus 2CO2 goes to 2CO2 plus 2H2O plus 2CO3 2 minus. And of course, look here, you can cancel stuff out, cancel that out, and then you end up with the typical fuel cell reaction that you've always seen. But you did have to go through and use this carbon dioxide. All right. Also, don't forget states and stuff. That's important. So just make sure that you're paying attention to really looking at any information given in the question in the diagram to how you do these half equations. Don't just be thinking, oh, it's on the data sheet, so therefore I just copy that one. It's not always that. You sometimes have to add other stuff and work out some other stuff. Okay? Right, that's it.